Okay, hello again. Our problem is trying to figure out where does this bell curve thing come in. Last time I talked to you about this move from using heights to using areas to indicate relative frequency or proportions. That from now on, well, very often we're going to be using the area of a distribution to represent proportions instead of the height. But where does this bell curve, this normal curve, sometimes called the Gaussian, where does it come from? Well, probably the best answer is something called the central limit theorem, which we'll be talking about really soon. But I'm going to make another shot at something, a little something that's a little simpler that also the bell curve, the normal curve, comes out of it. So see if you can follow along, if this makes any sense. So we're just trying to naturally see why our universe has the bell curve in almost every place we look. Okay, so try to follow along with me. Okay, get rid of that face. So let's talk about a person's height. Often we measure heights, and that is where we do a lot of our data and such. So what if we say, okay, 67 is about where your height is going to be for someone, that we had some way of looking and telling what your height would be if all things were kind of neutral or very average in that country. You know, it's half nature and half nurture, so just bear with me. It's a simple little model, okay? But suppose that as you go along, lots of little things happen in life where if it goes one way, you'll actually grow a little taller, and if it goes another way, it kind of bumps you down as to what you're going to reach eventually, okay? So that's what I'd like to think about. So, you know, maybe there's 30 of these events, or 50 of these events, or 100. I say 30 here. So maybe there's 30 of these events with each event may eventually end up with either losing or gaining a small little bit of height, like half an inch or a quarter inch. I certainly know that with age, each year ticks off at least a good eighth of an inch, if not a quarter. Okay? So what would that look like? So what I want to do is imagine the smallest case first. And like I said, it is a rough, silly little model, but I think you could kind of imagine this happening a lot. So what if we just had two such events, and each event made a difference of 6 inches in this person's ultimate height? So let's think about what could happen. Both events could go badly, and we'd end up taking 67 inches and subtracting 6 inches each time. The first one goes badly and we subtract 6 inches, but the second one goes well and we add and nothing happens. Vice versa, something goes well and then something goes bad and nothing happens. Or both things go well and we actually end up adding a foot, right? So there's 4 different values that can occur from that, just that having 2 events, each one affecting us by 6 inches. So what I've done is I just run a simulation. You don't have to run a simulation, but I ran a simulation, and as you can see, I'm using Mathematica so I can get the pictures pretty, because we're just trying to sit back and do a little learning. So I run a sample of 5,000, where in each case we start at a base value of 67, we flip a coin twice, a fair coin twice, and however it goes, we add or subtract 6 inches. And this is what we get. Just like we found, there's 3 things that can happen, and one of those things happens twice as much as the other 2. So 50% of the time we land at 67, and 25% of the time we land on a 55 inches, and 25% of the time we land on a 79 inches. And there's a nice picture of that. Okay? All right. So let's up the number of events, but let's pull down the effect that each event has on your eventual height. So I don't want to go crazy, and by the way, this has a name. All this is called basic binomial distributions. And if you took a regular, not regular, but a more advanced stats class, you would definitely see this distribution, because it's probably one of the most primary basic distributions. It's all about flipping a coin. Okay, so suppose we have 4 events and each event affects things by 3 inches. Let's look at what happens. Okay? So now it's kind of like a pyramid, right? We can have all 3 events being poor, all 3 events being great, but those are not as likely. Those are pretty extreme. And if you think about it, most of the time I'm going to either have 2 good and 1 poor, or 2 poor and 1 good. Right? So there seems to me that there ought to be 4 different things, but the software decided to make this density histogram. Notice there's no y-axis. This is a density histogram. Decided to make the bin width so that there are 5 different things to choose from. All right, so let's keep going. Now I want to do 12 events, and so I want to shrink how much each event affects the height by 1 inch. So I could have everything go wrong at all 12 events. All 12 times in my life things went wrong and I ended up with a whole foot taken from my height, or everything just goes right. All the nutrition, all the moments, all the things that were going on in my body, everything went right and I ended up adding a foot above my 67 inches. And all the things in between. And we'll talk about, there's another place where you've seen this kind of event. So what happens? Well, here's a picture. Again, I run it 5,000 times, do a density histogram. No need to trying to calculate. We could easily calculate the exact distribution, but why? Why not just run a sample and see what it looks like? Again, more pyramidal, I guess pyramid-like. How about that? Okay? Now here's my last one. Let's do 48 events, and each one has a 1/8 inch, 1/4 inch effect on our height. Now, it seems to me that in life, every day things happen that could affect how well we're growing, especially during our time of growth. So that number 48 might be a couple of hundred or a couple of thousand things, each one having a little effect. And probably each one isn't just 50-50 coin flip, or that the amount that each one affects our height is different from time to time. But those are all just more advanced models. So right now we got 48 events, each one affecting our height by 1/4. Let's see what that looks like. Okay? Now that doesn't look like a pyramid anymore. I think if we handed this to class and Dr. Taylor asked you, what do you see here, you would see a bell curve. Now here's what I'm going to do. I'm going to take a distribution that I know, that I call the normal distribution, and actually I shouldn't call it the normal distribution. There's a whole class of them. For every mean and standard deviation, there's a different normal distribution, but they're all bell curves. And what I'm going to do is I'm going to redraw this simulation here, this histogram. Now it's a density histogram. That's what's important, because the bell curve goes on density. It's the area that tells me proportions. It's the areas that tell me information, not the height. So I'm going to put behind this the normal distribution that has the same mean and standard deviation as this histogram. And let's see what we get. Look at that. Now, if you look at the mathematics of this, we understand that what's going on here as high and higher levels of something called the binomial distribution. And we know that there's lots of things in life that can be modeled this way, of where something finally ends up is lots of these binomial decisions that have little small effects, and then on the overall aggregate, this is where we end. And notice lots of things end up right in the middle, where it's very rare for all the events to go right and end up, or all the events to go right and end up on the tails. But the shape you get is this kind of bell curve. And it's not just a general curve. And that's what I wanted to show you at the end of this. I want to show you that we know exactly, we can mathematically prove that the binomial distribution, as you up the number of events, converges to a bell curve. It looks more and more like a bell curve. And I want to show you that this curve that I drew here wasn't by a pencil or anything. I actually curved it with a plot, and I'll show you the plot so that you can say, here's a curve that's centered around the the origin, and so it has mean 0. This is the bell curve, the normal curve, the Gaussian that has mean 0 and standard deviation 1. So this is called the standard normal. In all the bell curves, all the normal curves, I'm going to stop calling it bell curves, all the normal distributions, no matter what the mean and the standard deviation, can be shifted and squished or pulled or stretched to be exactly this one. So one of the ideas that we're going to learn is to get a z-score, which means that we're going to take whatever normal distribution you're playing with and translate it, the values, into terms of this normal distribution. And notice that the magic pi appears in the formula, but it's not a, it's just a, it's interesting that pi appears in this distribution that occurs all over the universe, but the biggest thing is that this is an exponential distribution, a type of exponential distribution where you've got e raised to a minus x squared, and that's what turns it down on each side, because the x squared is always positive, minus always goes down. Do you need to know that formula? No. Unless you want to be educated, unless you want to know, yeah, e comes up, and it's got, it acts like a big deal, and you see e to the minus x squared sometime, your head triggers bell curve, then good. You got it. Okay? Now, where else does this come up? If you've ever seen on The Price is Right, and I know I'm aging myself here, the Plinko game, that works on a binomial distribution. And it's, in general, it's called a Galton board. And maybe you can find one. Maybe you can look. I was going to show it on here, but I think you can find it. It would be worth looking, worthwhile to go find one. Go find some simulation where it's got basically balls dropping down or coins dropping down from the top, and you've got one nail and then two nails and then three nails and on and on and on, where each ball hits a nail and makes it decide, does it go left or right, left or right, left or right, left or right. Those are those binomial decisions. And then when it gets at the very bottom, they're collected in bins, and the stack of the balls form, if you have enough decisions up here in this Plinko game, this Galton board. And by the way, Galton was also one of the main people that helped us think about regression lines. So personally, not such a nice guy, but mathematically, he did some great stuff. And this board is named after him because I think he was the first one to present it. But it gives a nice physical example of a binomial distribution that converges to a bell curve. Okay, so look for a Galton board, and I'll post a video on how to do this z-score thing. All right? See you.